What's the first step in understanding it? What should you have done first? You have to draw a picture, right? And it wasn't trivial, but you ended up with two circles, correct? So the first part, which is not trivial, you end up with one circle right here. Which one is that? Again, that's a terrible circle. That's this one's. Which one's this? R equals cosine theta, correct? And then you end up with another one here, and that one's R equals sine theta, right? So what region are you trying to find? You're trying to find the area of that region, correct? And you should notice, theoretically, that what do you actually have? You have one region that's symmetric over theta is equal to pi over 4. Does everybody see that right there? So what integral are you talking about here? You're talking about, well, what's the height function going to be? What is it? R dr d theta. And what's r going from? Well, if you're going to, on the outside, if you're going to go to 0 to pi over 4, because what are you going to put on the outside right here? You're going to double it. What's the inner one going to be? It's this arc right here. So what's that inner arc going to be? 0 to what? Sine theta. So step 1, which was not trivial, was coming up with this graph. It's not trivial, but you need to come up with it. Then what's step 2? Writing the integral is the big step. Those are key steps there. You have to write the integral. You could write it as 2 if you wanted to. That's fine. Then what's step 3? Which is the hard part. I personally think step 3 is the hardest part. Do it. Actually evaluate the integral. That is correct. Actually evaluate the integral. Okay, so here we go. So we end up with 2 times 0 to pi over 4. And then you end up with what? 1 over 2r squared from 0 to sine theta of d theta. Correct? Right? This entire question comes down to this integration right there. Exactly. So what does this turn into? 0? Oh, sorry, not 0 to pi over 4. But if you evaluate this, what do you end up? What substitution can you make? Sorry. Yeah, 1/2 what? Yeah, cosine of 2 theta, d theta. This is the substitution you can make right here. Sine squared is equal to this.
It is?
Yeah, it is. Okay. My typo. Oh, look at that. I even have it in front of me. 1 minus cosine 2 theta. Nice. Okay, so yes, you did the intermediary step of substituting cosine squared theta and then substituting it in. Sure. Okay. Okay, what do we end up with here? You end up with 1/2 of theta minus 1/2 sine 2 theta. From 0 to pi over 4. And if you evaluate that correctly over the course of a couple steps, you end up with 1/8 of pi minus 2 is what you end up with right there. That's what you end up with. This right here is the same thing as doing 0 to pi over 4, 0 to sine of theta of r dr d theta. Sorry, plus pi over 4, plus the integral from pi over 4 to pi over 2 of what? 0 to what? Cosine theta of r dr d theta. The boundary changes, doesn't it?
Yeah.
The boundary changes. After you pass pi over 4, the boundary changes from sine to cosine. You've probably had way more experience with this than I have because you're all super awesome physics students. But we're going to do stuff that looks like this now. What kinds of questions are we going to be working on if I draw you a picture like that?
Torque.
What? No, no torque. We're past torque. No, no torque. What are we doing? Nope. Balance questions. How many of you have dealt with balance questions in physics? You have, because I'd imagine you've seen things like this. Center of mass. Raise your hand if you've studied centers of mass. What's another way to say center of mass if you're dealing with a flat surface?
Balance.
Balance point. Excellent. Here's the basic question we'll be answering. You have a surface. Imagine you have a piece of plywood. And you cut out a piece of plywood that's some weird shape. Where does it balance? At what point does it balance? The easy version of that question is if the plywood has the same density everywhere. That's the easy version of the question. What questions are we going to be answering? Where the density changes all over the place. So you're going to have a function that models density across a surface. And what are you going to find? The center of mass, which is also another way of saying the balance point. This example right here. Let's say that you have about this is where the board is balancing right there. And you want to use kilograms, is that okay? Let's say at a weight of 5 kilograms right here and a weight of 10 kilograms right there. So 5 and 10. Theoretically, this would be balanced. Oh, and you're also assuming that this board right here has an even density. It's the same weight everywhere. Otherwise, this question gets way more fun. How do you make those two things balance? If you haven't studied balance points before, it's okay because you have an intuition, I would imagine, about this. Oh, one at a time. Who wants to talk here? Jackie, go. How do you know if these two balance? 10d1 has to equal 5d2. So essentially, d2 has to be twice the distance d1. The product. Okay. So what happens if you have multiple weights? What happens if I added in, for example, on this same one right here, let's say I added a, let's say 20 kilogram weight out here, and I wanted to add, let's say I only had, let's make this, let's say that's D3 right there. How do I'm not placing it, so I want it to be balanced.
So the 10 and the 5 are fixed.
The 10 and the 5 are fixed. Yes, I'm sorry. These two are fixed. So we know it's balanced if this is true. If I add these to this system, what do I add to the system above? I'll give you, yeah, 20d3 has to, plus, I'm sorry, plus that side has to be what? From d4, right. So if I had values for d1, d2, and d3, could I find d4 to figure out what the balance point is?
You don't even need d1 and d2 because you already know that it's balanced.
Oh, you know, it's already balanced. Okay, if it already is balanced, that's correct. So, but if I move those around as well, as I'm saying. You did 7 times 1. Why did you do 7 times 1?
Because that's the magnitude of your weight times your x coordinate.
Great. Okay, and then what are you going to do next? Am I going to add something to those?
Yeah.
What am I going to add?
12.
12 times what?
Yeah, okay, 12 times
2. And what am I going to add to that?
14 times negative 4.
14 times negative 4.
And you're going to divide by the sum of the masses.
Ah, divide by the sum of the masses. Yeah, you've done this. So plus 7 plus 12 plus 14. And what is y bar going to equal? The same thing, but exactly 7 times 5 plus 12 times negative 2 plus 14 times negative 4, and we're going to divide by, yeah, the same mass. So this right here, you can think of this as, what's a really simple way of saying, what does 7 plus 12 plus 14 represent? Like the total weight of the platform. So theoretically, how many points are we going to look at? All of them, right? We're going to have some sort of physical object, and instead of placing weights on it, what are we going to have to figure out? The entire mass, because is the mass going to be the same at each point on this surface? No, it's going to change. So this, you can think of this as your total mass right here. And there are terms, there are names for each of these, but I wanted to figure this out. So if you do this out on your calc, you can come up with a fraction. Theoretically, where should that point be? Where should that point be located? Like in the middle, right? In the middle somewhere? So hold on. Represent right there. The mass. Just say the mass right now, okay? The magnitude of the mass, sure. And what does the 1 represent?
Position.
The position, the distance from the y-axis, right? The x-coordinate is the distance from the y-axis, correct? And you've done that each time. So how many times are you theoretically going to be doing it if you're doing all the points? In infinite, so what are we going to have to start using? Integrals. We're going to get summations, which turns into integrals. And apparently I went to recording it.